So let's try out actually finding some Taylor-Maclaurin polynomial problems. So this first one asks us for a Maclaurin polynomial, p sub 6, for sine of x to approximate sine of 0.1. So the first thing we want to do is we want to figure out where it's centered. And, well, since it's a Maclaurin, it's centered at 0. So the big thing we want to do is we want to start by finding out what the actual function value is at 0, what the derivative of that is at 0, what the second derivative, third derivative, fourth derivative, fifth derivative, all the way up to the sixth derivative. That's the kind of basis of what we need. So we're going to find f of 0, and since we're talking about sine of 0 is 0. Find f of 1, f prime of 0, which is, we have to be a little bit careful. So f prime of sine would be cosine of 0, which is 1. So now we do f double prime of 0. Second derivative would be negative sine. And negative sine of 0, I'm putting thetas in here, is still just 0. Now our third derivative at 0 would be negative cosine, which ends up being negative 1. So we are going to see, if we keep going with these, is every other term we're going to have a sine, and on the alternating terms we're going to have a cosine. And sine of 0 is always going to be 0. So the next term is going to be 0. And when you're doing multiple derivatives of sines and cosines, they alternate every two terms. So you end up with a positive, positive, negative, negative. So the next two would be positive. So we got positive 1. So f fourth derivative of 0 would be 0. F to the fifth derivative would be 1. And the sixth would then be 0. Okay, so what do we have? We start with f of 0 plus, and now we take our new f prime of 0, 1, and in general, if it was Taylor, it would be x minus c. But considering this is Maclaurin, our c value is just 0. So x minus 0 is x, and then we're talking about the first term, so it's the first power over 1 factorial, so we don't have to show those. And then we do our next term. So the second coefficient is 0, and then we have x minus c, so x minus 0 squared over 2 factorial. Well, what's going to happen to every even term? Every even term's got a 0 here, so they're all going to drop out. And all we're worried about is really the odds. And the odds alternate between positive, negative, and positive. So I really only have those three terms. So the next term would be the negative 1, and it would be x minus c cubed over 3 factorial. And then we do x to the fourth, which is 0, x to the fifth, so plus 1 x to the fifth over 5 factorial. Now, the sixth degree Taylor polynomial generally means that we go to the sixth derivative. We have a sixth power on there. But, however, the sixth derivative is going to be 0, so my sixth term is just 0. So it's not like for a sixth degree Taylor polynomial that we normally stop at 5. We normally would stop at 6. Our 6 is gone. So let's clean this up a little bit. So p sub 6 of x, our sixth degree Taylor-Maclaurin polynomial, would be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And that's true for every single Maclaurin polynomial that is centered around 0 for sine of x. Now, if I want to go further, I'm hoping we see that the next one would be minus x to the 7 over 7 factorial. Keep going. Plus x to the 9 over 9 factorial. Alright, so the goal wasn't really to come up with the polynomial, which is sometimes just a goal. We want to approximate sine of 0.1. Okay, so if we take 0.1 and plug it in here, p sub 6 of 0.1, we can really just plug in 0.1 for our axis. 0.1 minus 0.1 to the third over 3 factorial plus 0.1 to the fifth over 5 factorial. Now, most of you are probably wondering why in the world we're doing this. Well, the question is, do you know what sine of 0.1 is off the top of your head? You know sine of 0, and that's why we use the Maclaurin polynomial, because I can evaluate that. I don't know what sine of 0.1 is. I'd have to take out my calculator. And this is one of the things that the calculator does, is it computes them using the Taylor and Maclaurin polynomials. So it's not all that fun to calculate this by hand, or I could cheat and use my calculator anyway, but I could figure out what this value ends up being by hand if I so choose. So toss this in your calculator, plug and chug, and you get your answer, and it will be approximately what sine of 0.1 is. So I challenge you, do the Maclaurin polynomial for the sub 0.1, and do sine of 0.1 and see how close they actually are. So for us to actually evaluate the sine of 0.1 using our Taylor polynomial, this is what we have to do. We bust up our calculator, type in our 0.1 everywhere we saw the x's, and then hit enter. And we get this value. Now, one of the things we probably want to do is double check, is this actually close to what sine of 0.1 is? So we do sine of 0.1. Probably want to make sure our mode's in radians. I believe this one is, but let's double check. Yeah, it is. So sine of 0.1 is 0.0998334, at least according to our calculator. So we managed to get this correct to 2 decimal places. We're off by 1,000. It's pretty darn accurate. Another thing we can do is we can actually graph this and take a look at it versus the two functions. So in my y equals, I'm going to be putting in my actual Taylor polynomial, which was x minus, and then we had x to the third, and then it was divided by 3 factorial, which was 6, and plus x to the fifth, divided by 5 factorial, which is, oh, I don't want to write that, I want to write 120. So that's what we got, and we're also going to graph sine of x. And for, well, let's just graph them both and see what happens. And we're going to make our window go from, yeah, that's fine there, but I want to zoom in on the y's because sine only goes to -1 to 1. So let's go from -3 to +3 and see what happens. You can see them a little bit more clearly. So there's my Taylor polynomial. It doesn't look quite like a sine function, but here comes sine of x, and we can tell around 0 it's pretty darn accurate. It's pretty accurate between, I don't know, this interval here. Now at 0.1 we could tell that it wasn't quite accurate, but I can't really tell visually unless I zoomed in really close any difference. So one of the things that happens as you get a higher degree Taylor polynomial, you start matching more and more of these bends as you go along. So anywhere around where we're centered, and this one's centered at 0, we're going to be very accurate. Actually, at sine of 0, we actually have the actual function value, and it's not approximately, it actually is sine of 0. So that's what it looks like visually, and that's how you find the actual value. Now if we want to estimate sine of 0.2, as long as we're using the same function, same Taylor Maclaurin polynomial set around 0, all I would do is just plug in 0.2 everywhere I see 0.1, everywhere you see x. It's the exact same thing. Let's try one more Taylor polynomial here before we move on. So we want to estimate the natural log of 1.1 using the 4th degree Taylor polynomial. So the big question here is, where in the world is this centered? So we got to pick a center that's close to 1.1, but that we have to be able to take the natural log of it. So I don't want to try the natural log of 2 because I don't know what the natural log of 2 is in my head. We have to be able to take f of whatever the number is, f prime of whatever that number is. Like, we have to be able to do the derivatives and all that at that point. So it needs to be a useful point, and it should be one around 1. Well, natural log of 1 is 0. So we're going to center this around 1. So f of 1 would just be 0. F prime. Now we want to think of this as natural log of x. So f prime of 1 would be 1 over x. That would be f prime of x. So f prime of 1 would be 1 over 1. Or 1. Alright, let's see f double prime of 1. Here, I'm going to do my actual basic derivatives up on the left. I don't want that to be misleading. This is just 1. So this is 1 over x. So the derivative, think of that as x to the -1, right? Let's drop down your -1, so -1 over x squared. Okay. So at first it just looks like it alternates. -1, We need f triple prime of 1. Now, x to the negative 2, I drop down my negative 2, so negative 2, there's a negative up front, cancel out. X to the negative 3. Now all of a sudden I get a positive 2. A little harder to see the pattern in this one. Good thing we only got to go one more. Drop down your negative 2, so we end up with a, drop down your negative 3, negative 6x to the negative 4. Okay, so that gives us our negative 6, because x to the negative 4, if it's 1, still just 1. So we say a couple things. It alternates. 0 is kind of hard to say it alternates, but I think it goes positive, negative, positive, negative. I can see that because of the fact that I'm going to be bringing down a negative each time, it is going to flip, so it would alternate. So when you start to learn the Taylor series for the natural log, you'll see that it has to alternate. That's just true of how the exponents work. Alright, so let's see how it goes. So start with our f sub 1, so 0, plus, and then we do our f prime of 1, 1 times x minus normally c, and our c value is 1. Get into the first over 1 factorial. Not all that necessary because those are just 1s. Plus, and then we do our second derivative, negative 1 times x minus c to the second over 2 factorial. So we got 0, 1, 2, and we just go to the next one. The third be a 2, x minus 1 to the third over 3 factorial. And our fourth one is the negative 6, so negative 6, x minus 1 to the fourth over 4 factorial. Alright, so from here we want to estimate natural log of 1.1. So this would be our p sub 4 of x equals this. So this is our 4th degree Taylor polynomial. So to estimate it, we're going to take p sub 4 of 1.1. And we plug that in there. And 1.1 minus 1 would just be 0.1 minus, well, it's just a 1, so I don't need that too much. I get 0.1 squared over 2 factorial plus, leave the 2 out front here, 0.1 cubed over 3 factorial minus 6.1 to the 4th over 4 factorial. Just like the other problem, this is going to be approximately natural log of 1.1. So take out your calculator, list in your Taylor polynomial, put in your actual natural log of 1.1, see how close they are. And one of the things about Taylor polynomials, if you want them to be more accurate, just increase the degree. 4th degree is going to be good, but the 5th degree would be even better. 6th degree would be better, so on and so forth, up until you went to the Taylor series, which we'll talk about soon, which is all of them. And infinitely many terms ends up being no longer approximately, but equal to the natural log of 1.1. But you'll see that this converges very quickly to the actual value, so we don't need an infinite number of terms to get very good.